what was it that was necessary to consider. And two major parameters came out. There was convenience as well as efficiency. Those were the two major things that needed to be considered when designing an operating system. So we carry on with chapter 1, whereby we discuss these concepts. And as we carry on, we will see how different choices are available to the designer to choose from, depending on what design objectives they are targeting among the two. And what I mentioned yesterday is that in some cases, the two can be quite opposing. So the designer ends up lining more towards convenience, for example, rather than efficiency, or efficiency rather than convenience. There are some keywords we came up with when defining the operating system as well, that you cannot do without as you defining an operating system. We spoke, of course, about resource management program. We spoke about interface. The operating system plays the role of an interface between hardware and it's the one that ensures that they can talk to each other. So when I'm sitting, let's say, on word processor application, I get data from a keyboard, which is hardware. The data from the keyboard is going through an encoder, still within the keyboard. The data is being sent to the computer, and the computer has to pass it all the way to the application layer for the user to view. So that transition from all the way from hardware to the software application is handled actually by the operating system. Not only the operating system, but mainly the operating system makes that bridge between the two. It is, of course, seconded by other things in certain type of applications, such as APIs, application programming interface, which is a layer just on top of the operating system. But when you go from hardware to software application, the software in between is actually the operating system. Okay. I guess I could show quickly. Sure. Okay. I'll move closer again. I thought I was actually audible enough, or maybe what I can do is I can just remove the headset. I think maybe that's the issue. 1 second. We just want to switch off the Bluetooth. Okay, 1 second. Yeah, I think that way. Is it better? Just by show of thumb, you can tell me if it's better. Oh, perfect. So I'll stop using the headsets then. Sorry. Yeah. So I was just revising in short what we covered yesterday already as we introduced the subject. And today we now dive into chapter 1 basically in terms of its actual content and its different aspects. The objective of this chapter is to describe the basic organization of computer system. You will notice that there will be some repetition of things you might have learned already through computer architecture or any other related modules, mostly computer architecture. But it's important to emphasize the structure of or the organization of the computer, for example, for someone to understand how the operating system fits in. Okay. To provide a grand tour of the major components of the operating system, what are the key elements that form an operating system? So when we speak about operating system, there are some core elements that automatically we must think of. Then we give an overview of many types of computing environments, and we explore some open source operating system. Those are the objectives we are seeking throughout this chapter. Now, let's start with the abstract view of component of a computer system. So, and this here, of course, computer systems vary a lot, all the way from a microcontroller to a mainframe. through the personal computer, mobile phone, personal computers. They still have what we can actually refer to as the core, some basic things that they all have to a certain degree. And when we look at the computer system in general, you would normally have computer hardware. There's no computer without hardware. Then, as you can see, the interface layer, just on top of the hardware layer, we've got the operating system as the first software layer, because the operating system is actually classified as software. So it's the very first software layer on top of hardware. And on top of the operating system now, you have system as well as application programs. It's important to make the difference between the two. What you guys have learned to design in Java, in C++, and so on, HTML, etc., are mostly application programs. But there exist what we call system programs. And we'll learn a bit more about system programs as we study about system calls and so on, and how the operating system handles them. But just to give you a typical example of a system program is, and I will open one now. When I go, for example, to this Bluetooth application within this computer, if I open that is an app. Yes, it's mostly get installed immediately together with the operating system. So it's the type of most system applications, by the way, get installed at the same time as the operating system. But it's system application for the simple fact that it actually is almost part of the operating system, and it's directly it's not reconfigurable by the user. So it's not something in the reach of the user to a certain extent. Its modification or its modification or changes on it are not to the reach of the user. That's why we call it a system application, a system program. But that distinction will come much more clear as we go. But within this category, of course, you do get a lot of things depending on what the user does. At application program layer, you get a lot of types of applications. You get editors, text editors. We've got many of them. You can think of Notepad, Notepad++. You can think of Word, etc. You get compilers, IDEs, if this computer is being used by a programmer, for example. You get database systems, for example, and this here you think of SQL and many others, for example. And these are application programs that are directly accessible by the user within a computer organization. And this is very important to have this view in mind as we discuss operating system, because for example, I'll show you now a typical example. Let's go back to Bluetooth. From Bluetooth, we at the hardware point of view, what we normally have is that we have a Bluetooth modem within the computer. Of course, when we speak about a Bluetooth modem, it's not just the modem, it's the radio. Yeah, it's the modem. Let's call it the modem. It's made up of a radio, definitely. It's made up of an antenna, because Bluetooth is a wireless communication platform, so it requires an antenna, and other electronic circuitry. Right on top, we have the operating system. The operating system is a piece of software. Has got how can I put it? It has got key core functionalities that are related to Bluetooth, and this has to do so the operating system is the one that provides socket links, and here I'm referring not socket programming, hoping that you guys have done some network programming already at this stage. So it's the one that provides socket links, so to whoever is developing the application on top. So let's say you want to write your own application in C#, for example, or in C++, that will be sending files through Bluetooth. So what will happen is that from your application, you will speak to the hardware through the operating system by means of socket functions. And these socket functions will include one for opening a port, for example, one for closing a port, one for pairing, etc. Is that okay? And you at application layer, you are more or less just passing arguments or parameters to these socket functions or methods that are inherently built within the operating system. Okay, just to give an example. What operating systems do? We begin our discussion by looking at the operating system's role in the overall computer system. We need to, as much as we say it's the interface, it's the resource manager, we need to now critically assess its role and in details. Okay. A computer system can be divided roughly in 4 components. We've got the hardware, the operating system, the application programs, and the users, as shown in the figure above, of course. On the hardware side, well, you can't speak about a computer system if you haven't got a CPU, Central Processing Unit, of course. The CPU, within the CPU, you have the ALU as well as the control unit, as you know very well. I just want to connect the writing pad so that I can draw. Because that is what exactly a computer does. It does arithmetic and logic operations. Anything else can be scaled up. Can be scaled, any form of complex operations we know of can all be scaled down to those arithmetic and logic operations. If throughout your computer you are able to do, let's say, some integration of some sort, for example, that integration is at the end of the day a summation, numerically, as you've learned in math, I'm sure. So at the end of the day, what is happening is that everything is reduced to arithmetic and logic operation. By logic operation, we're talking about things such as ANDing, ORing, XORing, etc. Things that you covered in digital systems, of course. And by arithmetic operation, we're referring to your addition, subtraction, and so on. It's as complex as many operations we do on computers look. If you break them down, they end up just becoming your basic arithmetic and logic operations, as you know. So when you speak about hardware, especially in the context of a computer system, there must be a CPU. But not only CPU, there is also memory. Because a computer system indeed needs to store data, retrieve it. So when we speak about memory, we think of 2 functions, reading and writing. Writing for storage, reading for processing. And finally, when you speak about hardware, you must speak about input and output devices. Because computer systems don't just go alone, they normally linked to peripherals, mouses, keyboards, printers, etc. And this is done through ports, communication ports. So those are the 3 major aspects of in terms of hardware when it comes to a computer system. Why is it important to mention this? Because the operating system that comes as a layer just above the hardware layer needs to manage these. It needs to be able to manage the speed at which the CPU is operating as a way to give more convenience or user experience to the user of the computer. So a good operating system is the one that manages the processing task appropriately to ensure that the user get a seamless experience as they use the computer system, for example. So there's a management role in terms of the CPU that is being played by the operating system. Memory-wise, the same. Memory is broad, but it's limited at the same time. So it needs a good operating system will have to manage it properly. And we'll get to that specific aspect where we discuss memory management. But the portion within the operating system that is specifically dedicated for managing memory is what we call the file management system, part of the operating system. And there are many approaches to this, and we'll learn the different approaches. And as we learn the different approaches, then you'll get to know which one would choose in designing an operating system for a specific application. And of course, IOs. Okay. So the hardware provides basic computing resources. Is the keyword there is resources for the system. Then beside the hardware, we obviously have the operating system, as we mentioned, but on top of the operating system, we've got the application programs. word processors, spreadsheet compilers, web browsers, etc. And these define the ways in which these resources are used to solve users' computing problems. Because at the end of the day, we need a computer to solve a problem. And this problem is a computing problem. So for example, we need a computer to send an email. We need a computer to set up a test. We need a computer to write a contract, etc. So those are computing problems. The resources are mostly hardware, but the application program is actually there to define. So it's the one that defines the way we make use of the resources to achieve the solution to the problems at the end of the day. So the operating system is the one that controls the hardware, but also coordinates its use, the use of the hardware among the various application programs, because most computer systems are what we call multi-programs. A number of computer systems are mostly multi-programs, meaning there are multiple programs running on the same computer system, meaning these multiple programs must share the available hardware resources, and that coordination must be done by means of the operating system or through the operating system. Most modern computer systems are also multi-user. Let's say the case of a server. The case of a server which is running an operating system, those server resources, meaning your memory, your CPUs, there could be more than one, your GPUs, graphical programming unit, your video cards, your graphic cards, etc. Those hardware resources need to be managed among multiple users. Okay, so that is the type of role the operating system plays there. Very important to keep that in mind. So it controls the hardware, but also coordinates it among the various application programs for various users. That is the multi-program aspect, the multi-user aspect. That management of resources, of shared resources, is the task of the operating system. We can also view a computer system as consisting of hardware, software, and data. That's another way to look at it. Operating system, can someone tell me, if you view the computer system as consisting of hardware, software, and data, where does the operating system fit? Is it the hardware component? Is it the software component? Is it the data component? Rambuda?
I think it would be software.
Software component. Okay. The operating system provides the means for proper use of these resources, proper use, efficiency, in the operation of the computer system. Okay, so it's the one that coordinates who comes first. So, for example, you have Word as well as Excel open at the same time. Who accesses memory in priority and when, for example? All of that coordination happens at the level of the operating system, basically. Okay. So the analogy that is made, hence the analogy that is made here to say that it's like government. It coordinates things. Like a government, it performs no useful function by itself, meaning it's not the application, because applications is what programs are what are useful to the user at the end of the day. But it simply provides an environment within which other programs can do useful work. That's a very important statement there, which very well clearly defines the role of the operating system, the overall role of the operating system within a computer system. And as a being an operating system, it therefore coordinates operations. That's why we call it operating system. And which operations? Operations of application programs. Okay. So to understand more fully the operating system's role, we will now explore the operating systems from 2 points of view, from the user point of view and from the system point of view. Let's start with the user point of view. And this is all has to do with perception of what the operating system tasks and operations are when it comes to the user. In the user's view of the computer, there are many approaches to this, and it varies according to the interface being used. So as you go from a microcontroller, and I keep on mentioning microcontrollers just to draw your attention on the fact that most modern microcontrollers are now having also operating systems. You talk about your, this is what we often refer to as RTOS, real-time operating systems, okay? Okay. So depending on whether this computer system is a microcontroller or a mobile phone or a personal computer or a server or even a mainframe, you get different sense of what the operating system role is. So most computer users sit in front of a PC, which consists of a monitor, keyboard, mouse, and a system unit. By system unit, we mean the box, as we often refer to it, whereby within which you've got memory as well as the CPU being the two major components, and IOs, of course. Such a system is designed for one user most often. That's why we often refer to personal computer, because it's for one user. And this one user is supposed to monopolize all the resources. He can still be multi-programs. You'll use multiple programs, but it's one user in this case, or at least one user at a time, because it can be a shared computer, but you can be using it at the same time. So the objective in this case of the operating system, when it comes to personal computing, will be to maximize the work or play, in case of a video game, for example, that the user is performing. So you want to maximize that. So it's mostly convenience. If someone is working on Word, you want them to have a seamless experience, their typing to be fast, the typing to be clear and with no delays, and that's at the CPU point of view. And you want eventually them to be able to save what they're working on, that's touching on memory. And you want them sometimes to scan some things instead of typing them, for example. That's an IO type of example. You would want the operating system should be capable to ensure that someone, instead of typing, let's say, some serial number of a device, can just barcode scan it, for example, and that will type that serial number automatically in Word. So that will be the input-output interface there, input interface, sorry. And for another typical example will be printing. Printing is an output type of operation, whereby after someone has typed a document, might want to now release it on a printer. Okay. So in this case, the operating system is designed mostly for ease of use. So convenience is taking over efficiency when it comes to personal computer, for example. With some attention paid to performance, there's some attention paid to performance and almost none paid to resource utilization, because it's a single user. Now, how various hardware and software resources are shared, that is what we call resource utilization. In this case, at the user point of view, there is no sharing of resources. All the resources are dedicated to one user. So the operating system design is mostly focused in providing this one user an ease of use, of course, as well as, to a certain degree, some efficiency in terms of processing, so performance, but not designed to necessarily efficiently manage the resources, because they're not shared. Performance is, of course, important to the user, but such systems are optimized for single user experience rather than the requirement of multiple users. That is exactly what I just explained. But if we move 2 steps higher, meaning we go from personal computer, we skip servers and we go to mainframes. Mainframes are those huge computers you find in data centers. Okay. So if we go 2 steps back and we go all the way down to a mini computer like a microcontroller or a Raspberry Pi, okay, other users are accessing the same computer. If we start with mainframe, other users are accessing the same computer through other terminals. And it could be a remote server whereby the same server, meaning the same computer, through an internet connection, for example. Okay. These users share resources. So they are sharing the available memory on that server. They are sharing the available processing capability on that server, meaning CPUs. They are sharing the available graphical processing capability on that server, meaning GPUs, etc. So now comes in the resource utilization part. As you design this type of operating system, you wouldn't just consider the ease of use, you wouldn't just consider performance, lightly consider performance. You will consider performance very seriously, and you will consider resource utilization very, very seriously, because it's a case of shared resources. Okay, that is what I wanted to say. In still other cases, users sit at workstations connected to networks of other workstations and servers. These users have dedicated resources at their disposal, but they also share resources. So you could have a combination of both. You could have a combination of a user experiencing both shared resources as well as personal resources. So this is a typical case of within an organization of a user having to use, for example, Word on his personal computer, but having to use, let's say, Pastel Accounting, which is a software for accounting, on the server. Or even to give an example closer to you guys, having to use, let's say, Proteus Simulator through the TUT server, but Word on your personal computer. So you could have both shared and proper resources experience as a user. Okay, that is the case in which we often refer to workstations and server relationship in that case. So the user has got dedicated resources, but also shared. That is what I was trying to explain there. And that is, in that case, most often, these connected computers are connected through the network, of course, and this network can be wireless technologies or wired or even cellular. More and more, we also have mobile devices that are replacing desktop and laptop computers for people who are primarily interested in using computers for emails and web browsing. And not only that, as the word says, mobile device. So what a mobile device brings, unlike of different to a workstation, is that you can move with. And because you can move with, it doesn't have a lot of dedicated resources most of times, but through the network, it can tap into remote resources on servers, etc. So that operating system on a mobile phone will therefore not be the same as an operating system on a workstation, which uses most of the resources are dedicated. Okay, so that's why you normally have, that's why, for example, Apple couldn't just use Mac OS on cell phones. They had to come up with iOS, specifically designed for the mobile, as an operating system specifically designed for their mobile devices. Okay. The user interface for mobile computers generally features a touch screen where the user interacts with the system by pressing and sweeping fingers. You know how touch screens work. And that automatically makes a difference between the operating system of a workstation and the one of a mobile device, for example, because the one of a workstation does not necessarily have to be capable to handle a touch screen hardware. It's not built with that ability. At the same, but the one of a mobile phone has to be capable to handle any form of touchscreen devices, touchscreen hardware. Sorry. Yeah. So you see that those are the type of elements that make a difference at a user level in terms of how the operating system has to be designed. Some computers have little or no user view. Yes, you get computing devices with little or no user view. And this you can get with microcontrollers, for example, You might have a button linked to it, or maybe a fingerprint reader or something like that, but or a LCD display. That would be little user view, right? In some cases, you've got none. You might have a device to which you haven't got any user view, direct user view. You can only speak to it through the network or so. Yeah, the example is embedded systems, as I mentioned, meaning microcontroller-based systems in home devices and automobiles, even within cars. Yeah, they have numeric keypads, which is limited user view, unlike the full keypad that we have on personal computers, for example, which is alphanumeric, meaning it has got numbers, letters, as well as special characters. Okay, but the operating systems will therefore vary. What I'm trying to insist on is that it varies from one category of devices to another based on the required user experience. So the point here is really to say the design of the operating system is dependent on the user view. It's therefore dependent on the type of device at the end of the day. It's not a all-fit blanket for all type of devices. Now, when we speak about operating system, we can also view them from the point of view of system, at a system view. And from computer's point of view, the operating system is a program. As I mentioned, we classify the operating system as a software, most intimately involved with hardware. So it's a software very close to hardware. Since yesterday I mentioned the fact that when you design an operating system, you want to write it in a language that is programming language that is very close to machine language, meaning your assembly, your C at least. You wouldn't want to do operating system built in Java or C#, etc. Okay. In the system, when you look at the operating system in the system view or point of view, in this context, it's viewed mostly as a resource allocator. I would even say a resource manager to be more broad. As you know very well, management has to do with planning, controlling, and when you plan, you allocate. When you control, you check, and that's exactly what the operating system does. So it's a resource manager or resource allocator. A computer system has many resources that may be required to solve a problem. We've got CPU time, which is the access to processing resources. We've got memory space, access to memory, file storage space, okay, I/O devices, and many other resources we can think of. We can have network resources, etc. The operating system acts as the manager, exactly the word I was looking for, as the manager of these resources, facing numerous and possibly conflicting requests. So the operating system is the one managing a lot of conflicting requests, because it gets requests obviously from the application layer, application programs, and it has to manage, and it knows how much resources it has. So its task is then to channel or allocate those requests to these limited available resources. But when they are conflicting, it needs to come up with a solution with a solution to satisfy both requests to a certain degree, maybe one at a time, or there are many algorithms that are involved in the design of the operating system for managing conflicting requests, and we will study some of them as we go. So it's the one that decides how to allocate these resources to specific programs or specific users so that it can operate the computer system efficiently and fairly. The fair part. Every application must get a chance to access memory, to access CPU, to access resources, basically. Otherwise, that application is useless. Okay. Now, and these are the type of algorithms we'll discuss in this subject. How, for example, do we manage access to memory request to access memory from multiple users or from multiple programs. Okay, so as we've seen, resource allocation is especially important that where many users access the same mainframe or mini computer. A slightly different view of an operating system emphasizes the need to control the various input-output devices and user programs. So there is that understanding of the operating system as the manager, of course, but manager in the sense of controlling IOs. But most of times, it's at the system point of view, it's seen in terms of controlling other computer resources rather than IO devices and user programs. So it's mostly, the role of the operating system is mostly perceived in the sense of managing shared resources. Okay, so it's a control problem. Manager is still global because managing has to do with allocation, meaning planning. It has to do with controlling, as we are mentioning it now. So it's a control program. Yeah. So a control program manages the execution of user programs to prevent errors and improper use of the computer. It is especially concerned with the operation as well as the control of IO devices. Any questions so far? But most of this will make sense as we implement some of these algorithms in code. But it is important to place the basis so that you understand what we are dealing with. Are there any questions so far? Please, you must ask questions. If you don't understand anything, but if everything is clear, it's fine. But now, what is an operating system? We've said already a lot about the operating system, but this is just a formal definition of it. But now you probably see that the term operating system covers many roles and functions. I'm sure you picked up already that we sometimes refer to as an interface, sometimes as a manager, now a control program, etc. Although control is part of management. That is the case. Indeed, an operating system is quite a complex software. Because of the myriad designs and uses of computers. And so that's the reason why it's quite a broad concept is simply because computers have got a lot of uses. Okay, computers are present within toasters, like sandwich toasters, within cars, within ships, within spacecraft, homes, businesses. So because of the complexity of the use of computers, it's only natural that the operating system will, as a concept, will also have to be a complex system. Their computers are basis for game machines, music players, cable tuners, etc. There are many applications we can think of. Although computers have a relatively short history, they have evolved also rapidly, which gave or forced the operating system to evolve with, to keep up with that rapid change. Computing started as an experiment to determine what could be done and quickly moved to fixed purpose systems for military uses, such as code breaking, trajectory plotting, and governmental uses such as census calculations, etc. I don't want to dwell much into the history of computing, but yeah, it's important to understand where it came from, but so that you can understand that it is considerably changed, which had left the operating system with no choice than to evolve with it, because it's part and parcel of the computer system. Yeah, those early computers evolved into general purpose, to multifunction mainframes, and that is when the operating systems were born. So as we moved from basic computers to multi-purpose type of computers, then there needed to be an operating system to coordinate their action. In 1960, Moore's law predicted on an integrated circuit would double every 8 months. So you understand that at the hardware point of view, we're going from semiconductor to PN junction, which is diode, from diode to transistor, from transistor to logic gates, and from logic gates to microcontrollers, PLDs, PLCs, etc. And you go more and more complex. So in the early ages of computing, it was already predicted that there will be more and more transistors on ICs, which simply means there'll be more and more complex integrated circuits. And therefore, there was definitely an imminent role for a piece of software to manage or coordinate the action of these. Okay, and that is nothing but the operating system. So now, so how then can we define what an operating system is? In general, we have no completely adequate definition for an operating system. There's no simple way, but there are some key elements that must be part of a definition of an operating system. Operating systems exist because they offer a reasonable way to solve the problem of creating a usable computer system. So they're the one that make the computer system operational, usable. Okay, that's why they're called operating system. They coordinate the entire action. The fundamental goal of computer systems is to execute user programs and make solving user problems easier, because these programs are actually, that's the purpose of the programs. Computer hardware is constructed towards this goal. Since bare hardware alone is not particularly easy to use, you think about analog systems and how complex they were to use. Application programs are developed and they are more flexible and easier to use. These programs require certain common operations. Word, Excel, PowerPoint can both be written in two, meaning they've got something in common. So you wouldn't build dedicated hardware for each one of them, but you build one hardware that will be shared by all three, and that sharing will happen through the operating system, which will coordinate it. Okay. These programs require certain common operations, such as those controlling IO devices I just mentioned now, the keyboard. Okay. The common functions of controlling and allocating resources are then brought together into one piece of software, and that is what we call the operating system. Okay. In addition, so the operating system is coordinating the entire action, basically. In addition, we have no universally accepted definition of what is part of the operating system. A simple viewpoint is that it includes everything a vendor ships when you order the operating system. So it comes as a package. See, operating systems come as packs, like Windows often nicely put it. You might probably have heard about Windows, let's say 7 pack. So it comes as a package, and that package is a set of operations and functions that are the operating system will provide to user applications in terms of accessing hardware resources. Okay. So that's the idea. Okay, so the features included in the operating system, however, vary greatly across systems. That's why we've got different operating systems for different computer systems. Some systems take up less than a megabyte of space and lack even a full screen editor, whereas others require gigabytes of space, memory-wise here we're talking, and are based entirely on graphical windowing systems. A more common definition, and one that we usually follow, is that the operating system is one program running at all times on the computer. Is the one program running at all times on the computer, and this is what we often call the kernel. Because actions of the user are not synchronized, they're event-based, meaning they can happen anytime. There need to be some form of sentinel, something that runs the whole time to kickstart the action of the operating system, and that is what we call the kernel. Along with the kernel, now we are actually unpacking the content of the operating system or the different subsystems within the operating system. You can't speak about an operating system without speaking about a kernel. Okay, along with the kernel, there are two other types of programs. You get what we call system programs, which are associated with the operating system but are not necessarily part of the kernel, meaning they're not running the whole time, and application programs on the other hand. This is now higher than the operating system, at a higher level, which include all programs that are not associated with the operation of the system. So system programs are associated directly with the operation of the system, while applications are associated mostly with the user. Okay, so the matter of what constitutes an operating system, at the end of the day, the matter of what constitutes an operating system became increasingly important as personal computers became more widespread and operating system grew increasingly sophisticated. That way, it was becoming more and more important to have an operating system. Or the need for an operating system was highlighted even further with the increasing complexity of computer systems. And an example is given by 1998, the US Department of Justice filed suit against Microsoft, in essence claiming that Microsoft included too much functionality in its operating system, which then prevented application vendors from competing. Yes, exactly. Because Windows sort of, as an operating system, which was supposed to just end at kernel and system programs, became almost also an application provider. It also sort of started including application programs, because Microsoft will come with its own application programs, and then there was no room for application developers. Okay, so as the operating, this is just to show how the operating system went from as basic as the kernel, because essentially in the early ages of computing, the operating system was nothing but the kernel to a certain degree. Okay. So today, however, if we look at operating systems for mobile devices, we see that once again, the number of features that constitute the operating system is actually increasing. Especially with mobile devices, you get even more and more features. You will have a lot of features that you wouldn't have, for example, on a personal computer, and the operating system must still be able to handle that. You get more and more sensors integrated within computer system, within mobile devices than you have in a computer system, like your accelerometers, your in the past they used to be infrared. You have your Bluetooth abilities, your near field communication, etc. So because of that, mobile operating system often include not only the core kernel, which manages the typical resources, but was invented what we call the middleware, which is a set of software frameworks that provide additional services to application developers. For example, each of the two most prominent mobile operating systems, which are Apple iOS and Google's Android, features a core kernel. There must be a kernel, and I'm sure you probably have gone in the kernel of your cell phone. For those who are curious enough, it's normally a combination of your power on as well as your volume down key. When you press them, you see how basic a kernel looks like. It's more or less a console application to a certain degree. But that wouldn't work for mobile cell phones because of the type of use they have, the sensors they have, including the camera and so on. So you will have there was a need for more graphical type of application, but already handled by the operating system. And this is also because you don't want to install a lot of applications to do the basic features of a mobile device. So you don't want to be forced to install a lot of application. You don't want to force the user to install a lot of application before they can be capable or enabled to do basic functions of a mobile device, such as taking a picture, etc. So that's why mobile operating systems are often kernel with middleware, unlike personal computers, which are mostly kernel based and system programs. Okay, so these middlewares support databases, multimedia, and graphics, as I mentioned, cameras, etc. So that's it in terms of what operating systems do. And I hope you got the bigger picture there of what exactly is that operating system do. Typical assessment questions, for example, just to give you a glimpse of what's going on here. We have got two type of approaches as we assess in this subject, is that we ask questions that are more applied sometimes, whereby we give you a case scenario and you go from concept of operating system that we've learned and you identify the different components involved. The second type of questions we have are actually questions of implementation. So we come up with a system operation and you actually implement it in C and test it on a computer platform, in this case Linux. So those will be the two types of questions you should expect as we study this module. But of course, we also have comparison, discussion type of questions. Comparison has to do with selecting the best option at the end of the day. So we present multiple options to you. For example, we present to you the different algorithms that different operating systems use to manage memory. Then we give you a case scenario and you choose which one will be more appropriate. And because we will have defined for you what are the targets or goals or objectives in that specific system. Now, in 1.2, we look at computer system organization. I'll just introduce it and that will be it for today. Before we can explore the details of how computer systems operate, we need general knowledge of the structure of computer systems. In this section, we look at several parts of this structure. This section is mostly concerned with computer system organization, so you skim or skip it if you already understand the concept. Exactly, because you have most of times a dedicated subject for this, but revision is always important, and that's why we study this section still. But we look basically at computer system operation, how it operates, more or less like a step-by-step, all the way from the clock, CPU, memory, and so on. So that you understand that when you do a specific action at the application layer, what exactly is happening, what is the chain of events happening within the computer system. We'll also look at the storage structure, how is memory organized within a computer, that's very important. We will also look at the input-output structure, how the different modules interact with the CPU. That's where we tell you about the bus, the different architectures. You've got the Harvard architecture, you've got the von Neumann, which are two different bus philosophies. You know, we speak about data bus, address bus, as well as system bus, things that you normally cover already in the other modules such as computer architecture. Okay, so then we, in the end, of course, we speak about the architecture itself, and that is what we'll touch on next time. For today, that's it for today. I'll see you next time. Once we are halfway this chapter, I'll give you a tutorial, and then after that we'll have an assignment by the time we are done with the chapter. Any questions?
Okay.
Yes?
You forgot to upload yesterday's class on Brightspace.
Brightspace. So you couldn't download it from Teams?
Yeah, I couldn't download it from Teams because I did not attend.
Oh, I get you. Okay, I will upload today, both. Is that okay?
Yes, sir.
Okay, thank you. All right, I'll see you guys. Did you manage to install Linux?
Can you hear me?
Pardon?
No.
You must before next week, please. First, the virtual box So you can install it as a virtual machine so that it doesn't disturb your other computer operations. You install VirtualBox and then you install Linux on top, Ubuntu. I gave you the version, the latest version. All of this instruction is on D2L. Is that okay?
So, what if I have Ubuntu on the...
Oh, okay. If you already have Ubuntu, then it's fine. Then you don't need.
I don't have to download the VirtualBox?
No.
Oh, okay. And concerning the study guide, will you provide it?
Yes, I am providing it. We discussed most of its content nonetheless, but I still have to give you the document. In yesterday's class, we discussed the assessments and everything, but I'll still have to give you the hard copy. I mean, the written copy by this weekend, before next week.
Oh, and from the meeting yesterday, was it confirmed which mode you're going to use?
Yes. Good question. It's continuous evaluation.
Oh, okay. No problem. Thank you, sir.
Sure.